Hello everyone and welcome to Keeping Tabs on Chemistry. In this video we're going to be discussing solubility and saturation. So to talk about solubility and saturation, we first need to go back and review what we know about solutions and polarity. So in general, the solvent is present in greater quantity while the solute is present in lesser quantity. We know that solutes we've defined as the substance that is dissolved, and solvent is the substance that is doing the dissolving. So that kind of lends itself to the idea that the solvent is in greater quantity than the solute. So when adding a solid to a liquid, the solid is considered to be the solute, and the liquid is considered to be the solvent. However, not all solutions are solids and liquids. If both the solute and the solvent have the same state, so for example air, which has multiple gases dissolved in each other, the solvent is the part of the solution which is present in the greatest amount. So in air, the solvent is nitrogen gas, and then things like oxygen gas are considered solutes within that solvent. For polarity, polar substances, specifically polar liquids, are ones that will dissolve in water. Water is a polar solvent, so polar molecules can form attractive forces, those intermolecular forces with water molecules. So an example is alcohol, which is also polar. We know that alcohol can dissolve in water. Now, this obeys what we call the like dissolves like principle, saying if two things have the same polarity, they will dissolve in one another. So, polar will dissolve in other polar substances. Now, nonpolar liquids will not dissolve in water. Nonpolar liquids cannot form attractive forces with the polar liquids. They don't have the capability of forming those dipole-dipole forces. So, vegetable oil will not dissolve in water. The water is much more attracted to other water molecules by hydrogen bonds than it is to those nonpolar liquids by London dispersion. So, the two substances stay separated. So these liquids, however, will dissolve in other nonpolar liquids where they have similar attractive forces. The London dispersion forces of this other liquid are just as acceptable to the oil as it is to itself. So like dissolves like principle strikes again here, where if you have the same polarity, nonpolar and nonpolar, you can dissolve. So I have a joke here. What kind of bear dissolves in water? A polar bear. And here and here's a slightly disturbing Avengers Infinity War-esque comic for your viewing pleasure. But moving on. Defining solubility. Solubility is the amount of a substance that can dissolve into a solvent at a given temperature. So if we were talking about salt and water, how much salt can we dissolve into that water before it stops dissolving? So solubility is based on polarity, that like dissolves like. In order for a substance to dissolve, there must be attractive forces between the solute and the solvent. So, for the solubility of solid solutes, there are three major factors that can increase the amount of solid that we can dissolve in solution. The first one is mixing. By mixing, right, you're stirring up the pot and getting those molecules interacting with each other, which can allow you to dissolve faster and slightly more. So, by mixing, and in this case we have a stir bar, you end up getting a more even homogeneous solution. Increasing temperature will also increase solubility for the similar reasons. You're getting the molecules moving and interacting with each other. And finally, increasing surface area by crushing. When you crush something up, you're increasing the available molecules, the surface area for the two to interact. More interactions means more solubility. So we see these kinds of things in our everyday life. When you go to make a cup of tea, right? You don't just put the sugar in there and then start drinking the tea. First, you mix it to make sure that all of the sugar has dissolved. Now, you also, when you go to make iced tea, you usually don't ice the tea before you add sugar. You add the sugar into the hot tea because it's more able to dissolve in the hot tea than it is in the cold tea. Similarly, you don't put entire sugar cubes into your tea. Well, you could, but instead you use powdered sugar, something that has a lot of surface area and will dissolve quickly. All of these things go to increasing the solubility of the sugar in our tea, and we end up happily getting some nice sweet tea. Gaseous solutes follow some different rules. So the solubility of gaseous solutes actually decreases at higher temperature. This means that gas solubility is inversely proportional to temperature. And here's a graph that shows you as temperature goes up, gas solubility goes down. The reason why has to do with the kinetic molecular theory. Gases are very free to move. So, at high temperatures, you end up having more kinetic energy that the gases end up escaping out of that liquid to be free in the atmosphere rather than being contained inside of the liquid. So, as you increase temperature, your gases are actually more likely to escape. So this is why warm soda is not as bubbly as cold soda. Warm soda at a higher temperature means that the carbon dioxide dissolved inside of your soda is going to start escaping out more than cold soda where it's happily dissolved. Now, when we're talking about gases, we also need to be worried about pressure. So there's something called Henry's law that deals with the solubility of gases with respect to pressure. So pressure only affects the solubility of gaseous solutes in liquid solvents. So as pressure is increased, gases become more soluble. So gas solubility and pressure are directly proportional. If you think about it this way, if you have a gas suspended over a liquid that you are trying to force into this liquid, in order to maintain pressure inside of your container, if you push this down, so you increase the pressure on the container, then the gas inside has nowhere to go but down into that solution. This is the concept when you can sodas. The gas is put under pressure to dissolve it into your soda so that when you pull the tab here and break it open, that kind of sound that you hear is the carbon dioxide pressure being released and bubbling out of solution because it's no longer under that pressure. That's also why over time your soda goes flat because all of the CO2 will be released and you'll be left with no bubbly in your soda. Now, saturation. An unsaturated solution is one that can still dissolve more of the solute. So, if you're thinking about making your tea, maybe you don't want it super sweet, so you only dissolve the amount of sugar that you want. You could make it sweeter still, but you're choosing not to. So, what you're drinking is an unsaturated solution. Now, a solution that is saturated cannot dissolve any more of the solute at a given temperature. At that temperature, you have crammed as much sugar as you possibly can into your tea, and if you keep adding more, nothing else will dissolve. This is what happens when you add too much sugar. You can see when you get to the bottom that there's a pile up down there. That pile of sugar at the bottom is the sugar that could not dissolve into your solution. So you had reached maximum saturation and you were drinking a saturated solution of your tea. There's actually one more type of solution that kind of breaks the rules of chemistry. It's called a supersaturated solution. Now, this is one that contains more solute than can theoretically be dissolved at a given temperature. It's really cool chemistry because you have more than should be possible in there. So, how did they achieve this? Well, they heated up the solution to a higher temperature where you can dissolve more, and they dumped enough sugar or whatever it is in there to dissolve, and then they very slowly cooled the solution back down. And what happens is you get a very fragile solution where all of those molecules are still suspended and dissolved, but because they cooled it so slowly and there was not big changes in kinetic energy at a time, those particles stayed suspended and dissolved. So when you interrupt that solution at all, just by a shake or a piece of dust, all of a sudden all those extra molecules come crashing out of the solution as a solid and it forms a precipitate. This is actually how they form rock candy. You create a supersaturated solution and you input a stick or a like a popsicle stick into your solution, and all of the crystals latch onto that, which we call a seed, and it creates that precipitate directly onto your popsicle stick. You take it out and you have some sugar candy. So I have a video for you guys of, and it's not sugar, but a supersaturated sodium acetate solution. So you can see when they input it into the solution, all of a sudden all the extra sodium acetate comes crashing out, right? It can no longer be suspended. It's lost its kind of perfect situation. And they're going to do some pretty cool things and show you what happens. So you might be wondering, what does that feel like? Well, it's almost like a slushy, right? Where you've got crushed ice and things, so you can see they break it apart and it's got all that solid and just a little bit of liquid left. And they do some cool things like building like sand castles and whatnot. Now you'll notice once they connect it to the original solution and that solution has a seed, it all comes crashing out. So that is a saturated solution. Now, a solubility curve shows how much solute can be dissolved in a certain amount of solvent as a function of temperature. So you can see on my x-axis I have temperature, on my y-axis I have solubility in grams per 100 milliliters of water. So that's almost two variables, but not quite. It's saying the line is telling me what amount of solute the KNO3 I can dissolve in exactly 100 milliliters of water. So if you think about it, if this was 200 milliliters of water, everything on this graph would have to be doubled because I can put twice as much solute into twice as much solvent. So as temperature increases, you can see the solubility of the salt is also going to increase. Now we can talk about saturated, unsaturated, and supersaturated as three different points along this graph. If you are on the line, then you are a saturated solution. So say right here at 100 degrees Celsius, I can dissolve exactly 250 grams into this water. If I fall below the line, I am an unsaturated solution. So say at that temperature I only have 100 grams dissolved, I fall in this bottom section, I'm unsaturated. I could still dissolve another 150 grams to reach saturation. Now, above the line is where you get your supersaturated solutions. So, say you had 300 grams dissolved in that 100 milliliters, you've gone above the maximum. You are supersaturated. Now, how did they get to that supersaturated? They just kept heating it up to about 110 degrees, fit all 300, and then slowly decrease the temperature back to 100, and they have that fragile supersaturated solution. Now, solubility curves are not always that simple. You can actually graph multiple different salts on the same curve. So this is kind of a famous example of showing multiple salts all on one graph. It's saying the gram of your particular salt in 100 grams of water. Now remember, the density of water is 1 gram per milliliter, so this is the same thing as saying 100 milliliters of water. Now you might notice this little purple line here for cerium sulfate is actually decreasing in solubility. There are reasons why that happens, but it's above the scope of this course. So we can say in general, the solubility of salts increase, right, with increasing temperature. Now our final topic in this video is miscibility. Miscibility refers only to liquid-liquid solutions. So to be miscible, this is something that will combine to form a solution. So for example, food dye and water are miscible. They're both liquids, and when you combine them, you form a homogeneous solution. They dissolve in each other. So we would say that those two liquids are miscible in one another. Immiscible means that the two will not combine when mixed. So oil and water that do not have those intermolecular forces in common with another, they do not mix, so they are said to be immiscible. And that concludes our lesson on solubility and saturation.